Hi everybody, just as an intro, we're here with Carson Jace from LangChain. If you're here, you're most likely familiar with LLMs, and for sure LangChain is in your tool stack. This is one of the hottest tools right now. You should be working with that if you're not already. He'll be taking the stage. He'll be talking about his work there and some of the cool stuff that's coming. And after that, we'll have a short Q&A. Carson will be leading us, and I'll continue talking about stable diffusion and other generative AI applications. So if you're ready, Carson, just start.
Cool, absolutely. Thanks for having me, Rodrigo. I'm really excited to be here. Also excited to take everyone's questions. So I've got some slides that I'll try to go through in like 10, 15, 20 minutes, but really, excited to mainly chat about what you guys are interested in. So drop any questions in the chat and we'll try to get to them. I'm going to share some slides. Hopefully you can see this. And then hopefully when I go into slideshow mode, you can also see that. There, okay, that seems to be showing up. So today I'm going to be talking a little bit about how to build what we call context-aware reasoning applications with LangChain and LangSmith. And so, what exactly is context-aware reasoning applications? Why do you need LangChain? Why do you need LangSmith? So, backing up a bit, I think most people are so, you can ask ChatGPT a lot of complex and interesting questions, but if it needs information about data that it wasn't trained on, whether that be kind of like your personal data, whether that be up-to-date data, whether that just be kind of like ways of thinking about the world that you or your company kind of like take kind of like as instructions for how to think about the world, it doesn't know that because it's so general purpose. And so a lot of applications that we see being really valuable that are built on top of ChatGPT differentiate by bringing kind of like other sorts of context to the language model in a variety of ways. And that's how LangChain got started, actually. I was going to a bunch of meetups, chatting with folks, and saw some common abstractions in terms of the applications that they were building. Applications like all the ones listed here, where basically they weren't just using the language model as is, but they were bringing other sources of information to it, and then asking the language model to reason about stuff inside of that application. And so there's kind of like two big components, or two axes along which we kind of like see these types of applications being built. One is around one's around the context that's provided. So there's different ways to provide context, and then one's about kind of like the reasoning of the application. So if you give an input, how does it get to the output that it's producing? What are the steps that are taken in between those? And I think it's interesting to think about these because I think it gives you some view on the different ways that you can build applications and also the different difficulties associated with them. So jumping into it a little bit, there are a few different ways that we see people bringing external context to language models. And so I'm going to run through those four in a little bit right now. The first is basically prompting, and specifically kind of like instructions that you're giving to the language model. So instructions on how the language model should behave, on the output that it should respond in, the different ways that it should write a paragraph or something like that. So basically, the first set of context that is being brought is this instructions for how the language model should behave. This is kind of like if you show up on the first day of work, you get maybe like an employee handbook or something like that that has a list of rules on how you should behave. And so prompting is kind of like the first way to bring that. Another way to bring context is through the use of like few-shot examples. And this is basically providing examples to the language model of example inputs and then how it should behave when giving outputs. And this is a little bit different, even though these go in the prompt, these are a little bit different than kind of just instructions. And I think like one useful way to think about it is prompting is basically, prompting as mentioned before is basically telling someone or we're telling the language model how to do something. Few shot examples is like show, don't tell. So it's showing people how to do a particular task. Maybe the most kind of like commonly talked about way to bring context into language models is through basically RAG patterns, where you do some retrieval step and then you augment the generation and you basically ground the generation in that context. And so this is also a little bit, this is just a different type of context than the previous ones. It's not instructions on how to behave, and oftentimes these are all used in conjunction. But the kind of like retrieval aspect, it's not necessarily used as instructions for how to behave. It's not necessarily used as examples for how to behave, but it's used as content that the language model should ground its response in. And so you've got that type of content that you're bringing to the language model in context. And then finally, we've got fine tuning. This is basically taking any and all of that information, whether it be instructions, whether it be examples, or whether it be context, and it's baking it into the model weights and fine tuning the model weights. And so this is another way to bring context to a language model application. And again, these are all different techniques that can all be used together. And they have different purposes, and they have different strengths and weaknesses. And so it's not necessarily that you should choose one of these, but you should be aware of them and know when to use them and how to use them. The next aspect is this like reasoning aspect, which I'm going to kind of define as basically you've got an input, you've got an output. What goes on in the middle? How do you get to and specifically the middle of your application? So what's going on inside your application? And this is a little bit more, there's kind of like different levels. So there's, and kind of like increasing in what I would call like autonomy of the system. So the first level, you just have a simple LLM call. You've got some input from the user, you maybe add in some context, you then make an LLM call, and you return to the user. And it's pretty straightforward. It's fast, it's simple, but there are obviously a lot of disadvantages. Namely, it's a single LLM call, and so you can't do some of the more complex stuff, and it starts to break down when you ask it to do more complex reasoning tasks. Chaining basically combines multiple LLM calls or an LLM call with a call to a tool and then back to an LLM, and so it's combining multiple calls inside the application in order to arrive at its final answer. And so a good example of this is GPT Researcher, which is an open source GitHub repo that basically writes research reports. And so inside this application, what you've got going on is you've got a whole chain of basically one LLM that generates a bunch of questions. You then do search queries, you then summarize them, and then you write a final report. And importantly here in chaining, the steps are kind of like fixed. So you do this, and then you do this, and then you do this, and then you do this. And it's kind of known that the path that you're taking is kind of known ahead of time. Let's compare that to routing, where basically you use a language model or any other kind of like mechanism, although oftentimes happens with a language model, to decide which path to take. So there's a finite number of paths, and they're known ahead of time. But it's not known which path exactly will be executed for a given input. And so if we look at GPT Researcher, I lied a little bit before. It's not exactly kind of like a chain. There's actually some routing that happens. So specifically, this report agent, this actually uses different prompts under the hood, depending on the type of question that's asked. So based on the input, based on the type of question, it does some steps, and then there's basically like there's like a like science research report, there's like a technology research report agent, and it kind of gets routed to the correct one. And so there's still kind of like this finite set of paths, but it gets routed to the correct one. If we go into the next style of reasoning, we can now see that there's this concept of kind of like a state machine or automaton, and this is kind of like defined as there are states that are known ahead of time, but you can now have cycles. So you can have these cycles in states, and I'll go into some concrete examples of this, but the key differentiation between this and routing is that you have cycles. And so there's now technically kind of like an infinite number of paths that a given input could take. And so one example of this is plan and execute. So in plan and execute, you've got these different states that you're in. So you could be in an execution state and have an execution agent. You could be in a task creation state and have a task creation agent. You could be in a prioritization state and have a prioritization agent. And then you see that there's these predefined transitions between these different states. And then eventually, I actually don't know if this I don't know if this diagram has an exit function, but eventually you'll kind of like end. Another example of this is reflexion. So here we can see that there are actually 3 different states within the agent. There is an actor state, which decides what to do. And then there's an evaluator state, which can evaluate its trajectory. And then there's a self-reflection state, which basically reflects and updates experience. This is like the most common architecture that we see in some of the real world agents. And so this is taken from sweep.dev, which is a real world coding agent. And it's very much this idea where there's different states: search, plan, execute, validate. There's this cycle between states. So search goes to plan goes to execute goes to validate could go back to plan, or it could end. It kind of like depends. And so you have these states that it cycles through, and it comes up with a final answer that way. And then the final one is basically a fully autonomous agent. So the differentiation between this and the automaton is that there's not necessarily these different states that happen. It's all kind of like left to a single agent, a single LLM call, to go execute an action, get back its action, and then execute the next action. And so you're basically having this single LLM call do the responsibility of planning and then thinking about how to execute and so on. And so there may be like implicit states, but you're asking the LLM to take on these implicit states. And the current state is that most LLMs aren't good enough to cycle through these implicit states in their head. And that's why architectures like this, where you explicitly define these states, are a lot more powerful in building applications that actually work. There's a lot of difficulties with building context-aware reasoning applications, and so I'm going to talk about these, and then I'll end my chat and take questions. The first one, the main one that LangChain kind of like strives to solve, is the orchestration of all these different paths that you can go down. And so LangChain provides we provide kind of like a way to compose chains in different kind of like architectures. And then we also have a bunch of pre-built architectures that you can use off the shelf. So the goal is to make it as easy as possible to experiment with lots of architectures as well as define your own. Next, a big challenge where we see people spending time is with data engineering. So a lot of this is bringing the correct context to the agent, and that context is data. And so making sure that you have the correct data present, making sure that's flowing through the system in the correct places. This is a big this is a big part of where we see people spending their time. And the last part is around prompt engineering. So at the end of the day, a lot of this comes down to language model calls. You got to tell the language model how to do. You got to do things. You got to combine those different parts of context into a single prompt. And so there's a lot of art and iteration that goes into prompt engineering. And so all these screenshots that I've shown you have been from our platform LangSmith, which really helps debug all of these different things. So it helps debug what exactly is going on under the hood of your architecture. It helps debug what exactly does the data look like by the time it's going in and flowing through your system. And it helps debug what exactly is the final prompt, and then how you can, it allows you to easily tweak the prompt so you can see kind of like the changes for a given step. There's other things in LangSmith as well that solve some of the problems that we see. So evaluation we see as a huge pain point. Like, these context-aware reasoning applications are doing really complex things, and it's not at all clear how to evaluate them. And so there's some tools in LangSmith that make it easy to collect data sets and then run some common types of evaluation, as well as to define your own evaluations that you can run over data. Collaboration also starts to become more of a thing. So one of the things that we're noticing is that as these like complex systems grow, you basically have multiple teams and multiple different personas working on the same system. And in particular, you might have product people or business people or subject matter experts that are doing a lot of the prompt engineering, but there's still all this data engineering that you need data engineers or engineers to go do. And so one of the things that we recently launched is the Hub, which is a way of basically storing and collaborating on prompts to kind of like facilitate this cross-team and intra-organization collaboration. That's all I've got for today. I'm happy to take questions for the rest of it, happy to dive into any of those parts that were not super clear. I know there was a lot. And yeah, thank you guys for tuning in, and thank you, Rodrigo, for having me.
Thank you very much, Carson. While the audience actually can start with a few questions, if you don't mind, I actually have a few. You mentioned LangSmith. If people want to use that, how can they do that? Can they set that for their organization, their teams? How do someone get started with LangSmith?
Yeah, absolutely. So I'll drop some links in the chat, but basically LangSmith right now we have in a private beta. And so there is a waitlist, and I'll drop the link in the chat there. And then if you want to get off the waitlist, we will more than accommodate that. So just shoot us a message at hello@langchain.dev, and I put that email in the chat as well. And maybe include something that you attended this awesome meetup by Marvik, and we'll let you guys off the waitlist ASAP. And then once you get in there, you can create organizations. Right now, it's limited to up to 5 people. Although if you guys have large organizations, again, just reach out to us, and we can figure something out.
Perfect. I think we are starting to have some questions on the chat. Do you want to take it from there?
Yeah. So I see one from Pablo. Does LangChain include tools to build automatons agents? So if we think about the 5 different levels, first, LLM calls. We have a lot of tools for working with LLM calls. We've got prompt templates, LLMs, and output parsers, and that's kind of like the core block for working with a single LLM call. Next level is kind of like these chains. We've got a bunch of pre-built chains. We've also got this expression language, which is a way of easily creating those chains. Next, we've got a router. Here we have some functionality, although this is actually something we're working on internally to beef up a lot and make sure that it's really, really clear how to use this. We think this is one rough part of the framework actually that we're working to improve. Next, you've got automatons. We currently have nothing for that. That's something that we're working on again. And that kind of came out of doing this exercise, is trying to think through what the different states are. And so I think like within a week or two, we'll have something for automatons. Agents, we do have something for. So we have the agent executor. This is like one of the, this is a simple, it's a React style agent that loops. We've added a lot of handling for like errors, retries, things like that. And we've had that honestly from the beginning. And so there's pretty good support for that. It's kind of this weird thing where people kind of like, started with LLM calls, then with chains, then kind of went all the way to agents, and now we're like coming back somewhere in the middle, or at least that's the path that we find ourselves taking. Maybe we got too excited by the possibility of agents, but now we realize that there's some more structure that's kind of like needed to make things work. Good question. Would you mind sharing some real-world examples of chain and routing? Yeah, absolutely. So, I think some of a lot of the RAG-based applications, I'd say, are basically chains. Particularly like a common workflow is you have a conversation that comes in with, and then the final thing, the last message in the conversation is a user question, and so you want to look up documents relevant to that user question. The first step is basically to use an LLM or some other process to kind of like condense that conversation and come up with some search words to search for. You then search for those things, you get back a list of documents. Then you make another LLM call with the conversation history and those documents, and you get back an answer. And so that's a really, really simple chain where there's basically 3 steps. There's like a generate search query, there's a do the search, and then there's the generate the final response. And so that's a simple example of a chain. An example of a router could basically be even as simple as if you have kind of like 2 different search indices that you could look against. So maybe let's say you have Google search and you have like your own internal document search. And so then basically what happens at the query time, you not only specify like what query to look up, but you also say, hey, do I want to look up in Google or do I want to look up in my internal documents? And so now there's some branching that happens. And again, like the routing's known ahead of time, so it's either this or it's this, but you don't necessarily know which until the input comes in. Other examples of routing that we've seen are basically depending on the user question, you might want to use a different prompt to answer. So if they're asking about like math, you might want to use a prompt that says like, you're a math genius, answer this question. If they're asking about English, you might want to use something that's like, you're Shakespeare, answer this question. So that the prompt routing is a really, really common use case of routing that we see. Could you explain a little bit about how you approach the evaluation of systems based on LLMs? For example, if we change the version of LLMs in the backend, can we expect different results? Yeah, I mean, evaluation is really hard. Yeah, largely because, well, one, like evaluating LLMs by themselves are difficult. And then two, like you've got these systems built on top and the LLM's just one piece and it could change in the back end. The main way that we've found that's good to do this, one, you've got to assemble a data set. Like you've got to get a data set of examples and example inputs and example outputs. And you can do this either by having subject matter experts come up with it, or by collecting it from the wild if you launch a first version of the application and are able to collect results, or by generating synthetic data. So basically, you now have this data set. Then what we see being promising is you kind of like run your chain or agent over that data set, and then you look at the results. If you want to automate it, we've found we've found decent success in using language models to automate some of it. So using language models to evaluate it, there's actually a great article by Databricks about this today that I think referenced some of the techniques that we used, and I need to read a bit closer because there's a lot of stuff there. This is still a very open field. But yeah, basically my main advice would be start building this data set to evaluate on and start running it over when you're changing the language model, when you're changing the chain. And then step two is I would look into some of these like LLM assisted evaluations and using LLMs to grade the responses. How about other than English language support in LangChain? Many predefined prompts and tools are intended for English. Yeah, this is a really good point. And this is also part of the reason why we introduced the hub. So the hub is a way to share kind of like prompts, not only within your organization, but with the world as well. And so we've already seen a few prompts. I think there are a few kind of like in Chinese that are aimed at kind of like working with non-English applications. We don't really want to add these to the library because it quickly becomes like there's going to be a lot of stuff in the library, right? And so that's part of the reason why we added the hub, so that people could easily add kind of like their own prompts in their own languages, share them and discover them that way. Integration of LangChain with OpenAI is very thorough, and I was wondering if that kind of integration is also developed for Llama 2. Yes, like we've been putting a lot of effort into non-OpenAI integrations. And so, I think as evidence in the playground, in the playground of LangSmith, we support OpenAI, obviously. We also support Anthropic now. And then in a few days, we're going to support Vertex, Azure OpenAI, and Replicate. And we're also thinking of other open source models that we can work to support there. I think part of the issue with Llama 2 is it's not necessarily even Llama 2, it's like, how are you running Llama 2? Are you running it locally? Are you running it through a cloud provider or something like that? And so we have over 50 different LLM integrations because there's now so many different ways to run these open source models. And so hopefully one of those 50 should meet your need. I think as we see the ecosystem starting to mature, like, we see people using Anthropic a bunch. We see people using Google Vertex a bunch. We've seen some people using Replicate. We see a lot of people using Azure OpenAI. Like, we're kind of seeing what people are using and then making the integrations like really, really good for that. So if you guys have particular hosting providers or ways of running models, just let us know and we'll work to improve the support for those. We see a lot of experimental applications, but not too many get to production at scale. What does larger applications and production have in common? Do you have any tips for that? Yeah, that's a really good question. This is something that we're digging into a lot right now. I think the main things that they have in common, they're usually not like fully autonomous agents. So they're not those kind of like level 5 agents. They're usually they're usually, they're honestly usually like 2 or 3. One we see a lot, but people don't need to necessarily use LangChain for even that. I think LangChain starts to provide value for 2 and 3. 4, I think we're starting to see more. 5 still really, really rare. So I guess my answer would be like, the thing they have in common. And then also my tip would be to like constrain it a bit more, like really think about like what business constraints you can put on it. The other thing that we see is like they're usually customized. They're usually not using LangChain like as is off the shelf, and that's you know that's good basically. Like we have a lot of default prompts in LangChain, but those are just that, they're just defaults. Like for your own application, you're going to need to customize the prompt, and so we see people, and my tip to people would be to like really put effort into customizing the prompt and learning how to prompt engineer and learning how to work with that. And we're doing we're trying to make it easier on our end to substitute in those prompts as well. And then the other thing that I'd say is that usually people in production do like like a hesitancy to go into production is that people don't know how the application is doing. And so usually people in production have some mechanism for determining how the application is doing. And so that's some semblance of like a test data set that they're kind of testing against. And then that's also some semblance of monitoring and tracking what's going on so that they can tell how the application is kind of like performing.
That's perfect. I think we don't have more questions at the moment. I know that you also have a tight schedule, Harrison. Thank you very much for your time. I'm not sure if anyone else has an additional question. Harrison will be leaving us in a few moments. There we go. I think we have a new question for VAG applications. Do you have any particular preferences regarding the vector database?
Yeah, this is a really good question. So I would probably say it kind of depends like what you're going for and what you're building. And what I mean by that is like for some applications, you kind of just want to be able to do like so like for some applications, when I get started, I often use an in-memory vector database, basically, whether that's Chroma, whether that's FICE. FICE isn't necessarily a vector database company, but we have an integration with that. There's like a Docker array that's an in-memory one. So I use an in-memory one just to get started quickly, fewer dependencies, no network calls, zero cost. After going to production, it depends a little bit. Like we see a bunch of people using Pinecone and Weaviate, and I think those are maybe like the two largest pure vector databases. But we also see a lot of people using Postgres or Supabase or Redis or Elasticsearch. And I think the benefits of that would be a lot of people already have that infrastructure in place. This is also obviously like a very hot topic, and I think it's a little bit unknown what the best vector databases are. Whether you need a vector database or other kind of like databases will do the trick. I think it's early days here, but that's kind of like my workflow. I usually start with like Chroma or an in-memory one and then transition. We personally don't have kind of like, actually we have Postgres running for some stuff, but I think when we like we use Weaviate and Pinecone when we need something that's hosted and not available. But a lot of the larger enterprises that already have this Redis setup, this Elasticsearch setup, Postgres setup, like we see them doing that. So it's a little bit, there's a reason there's 50 vector databases. There's a lot of different factors to take into account and a lot of different use cases.
Great, that's great advice. Thank you for those, for sharing all of this information. Guys, we'll leave Harrison continue with his business. Thank you very much for joining us today. It was a pleasure having you here. For all of the others staying here, we'll be talking about generative AI and stable diffusion applications. Thank you very much.
Thank you for having me, Rodrigo. And thanks everyone for tuning in.
So I'm actually sharing my screen right now. Let me know if you can actually see this. So the other stuff we'll be actually talking about is generative AI using stable diffusion models, and production pipelines. We'll be talking about some of the applications we have built, some of the technology we are actually working with. Stable diffusion, in case you're actually not aware of, is those really cutting edge models that create those amazing outputs mid-journey, for example. Stuff like the one that we're actually seeing here. Diffusion comes from the technique that we need to do to create these models. We're going to dive into that. basically, the main takeaway, if you're not familiar, is that we can actually use text or data from woman with some details, as we're actually seeing here, to generate these amazing outputs we can actually see from this noise we have on the left. And just to highlight a few of the main features of this is that you can actually inject many things. You can have a lot of control because of the huge data sets these things was actually trained on. Here we can actually request illustrations and we get those outputs. And we can talk about these diffusion models without getting a little bit into GAN networks that are in a way what was here before that. GAN networks have really amazing outputs. They were really famous for creating these amazing facial images that really look like real persons, but are actually just generated out of noise as well. GAN networks, in case you're actually not too familiar, are actually really hard to train. And one of the main challenges we have with that is that features are entangled. And one of the most classic examples in this, if you want to generate the face of an old person, that old person is going to most likely have glasses. And that's something we can actually gain with diffusion models. GAN networks, the main how we can actually control those, we usually work with latent spaces, vector spaces. Here we have the red dots and the blue dots. We can actually find a separation in that vectorial space we usually work with. We run that through a generator. We won't get into the details of that right now, but with that, we can actually generate different faces in this example, but it can be basically anything that we're trying to generate. The GANs will actually try to mimic the training dataset we have to generate similar outputs. Having covered that, we'll dive into the diffusion models and some of the pros and cons of this. The pros, this is really state of the art. This has actually the best outputs in the market right now. These architectures really can have mind-blowing results, as we're actually seeing here. Midjourney's output for a dog. This is really realistic. A few years ago, if I showed this to anyone, it would be impossible to actually figure out that this was actually made by a computer and that this dog doesn't really exist. They're really realistic, also quite flexible, and you can leverage foundational models, same as we can actually have with LLMs. The cons from this, they're really expensive to train from scratch, and they share this with GAN networks, but it's way worse here. Inference is slow, and that can be a problem for some applications, and it's also costly to actually host hardware for this. And diving a little bit more into the training and inference data pipelines for all of this, how does this actually work? On training, these diffusion models, stable diffusion in this particular case, we'll try to generate. We actually have two important processes here going on, the forward diffusion and the reverse diffusion. Here we have the image on the left, that flower, and we have noise on the right, and the forward diffusion, it's a process that actually translates that image with subsequent steps into that noise we see on the right. And the reverse diffusion, it's the opposite. I think you can actually get an idea of how we'll actually try to use this, but basically we'll be progressively adding noise in multiple steps. As I was saying, that step is actually conditioned by the last step. We usually add Gaussian noise to all of this. This is quite standard in the field. And we'll be saving all of those partial images, because with that, we'll actually be building our training dataset. So during training, we'll execute this forward diffusion process that will actually add this noise to the entire dataset. And with that, we'll be able to create before and after steps in all of this. We'll use all of this to train a denoising model. This is basically those pairs from the middle steps, and it doesn't necessarily need to be the first image and the last image in all of this, but we care about all of the middle steps in that. So from one single forward diffusion, we can actually create a bunch of images, of pair images. We'll be training a unit network to try to predict the amount of noise added in the previous step. We can actually try to predict the amount of noise added or how the image would look without that noise, but we'll be basically training that unit. In case you're actually not familiar, that comes from the architecture with these connections that we have from the first layers to the last layers, and subsequently this unit network was actually quite famous a while ago, especially working with medical images when it was first launched. And we'll be really interested in the reverse diffusion process, where we'll be basically trying to deconstruct that noise. We train to use that unit. We train to predict the noise we added. And with that, we'll be able to take that noise we have as an output from the previous step into the original image. If you get the idea, we'll be then trying to use that noise that can be randomly created to generate really realistic images. So we'll be basically trying to reproduce what happened in this step in the middle. And in production, I like to talk about the applications, the industry, how this actually connects with all of that. And it's easy for me to talk about some of the problems we're actually facing with this. So we're actually building a virtual trial application. This is actually combining in practice Stable Diffusion and GAN networks. The problem that we're actually trying to solve is to virtually address any person with any garment in our catalog. So we're basically an e-commerce site. Some of the challenges we face with this is that we're actually aiming for pixel perfect quality, not just good enough. It really needs to be perfect. We also need to keep the identity of the garment and the person. This is really hard, especially with the diversity of persons and also garments, skin tones, light conditions, body shape. We need to take care of all of that. And there's, of course, a trade-off between higher quality and cost and time in all of this. And I'm not going to get too much into the details, but this is just one of the papers we actually based our work on. This is Beton HD. You can actually look this up. It's a really complex computer vision pipeline that actually has many steps, like segmentation, post-detection. You can see that on the top left, for example. And some of these models here are actually units, and we're actually using Stable Diffusion and GAN networks combined. All of this is actually based on this architecture. This is the Stable Diffusion architecture base, let's say, where we actually have the pixel space here on the left. These are actually the images. We actually train a variational autoencoder. This is the encoder and decoder we actually see with the epsilon and the D or delta, I'm not sure. We actually translate the images into vectors in this latent space. We see that on the green side. We do that diffusion process, and we do the diverse diffusion. And for the reverse diffusion, we train these denoising units we see here. We actually execute the inference through that unit a bunch of times because we actually have multiple steps in all of this. And what's really mind-blowing from all of this is the control we can actually inject, and not only the quality we can actually get from the output. And we do that with this conditioning on the right that's injected into the cross-attention components we have in these units. That's basically trying to guide the model to generate the images we want and not just any image, because remember, we're actually starting from noise and from that trying to generate a high quality output image. And just a little bit of history in this, we initially had the diffusion model, and we actually had a classifier that actually tried to guide the diffusion process so as to get the images we wanted. We actually used a separate classifier for that. This was really inefficient because of many things, but it's also less effective. The quality is actually not that good because we actually need to deal with a lot of noisy data because of the nature of this reverse diffusion. And then state of the art evolved a little bit. It actually didn't take that much time to get there. And we actually injected the guidance, that classifier model in a way, into the diffusion model. It's like built in. And this is great because we can actually be more effective and efficient in all of this. I'm not going to get too much into the detail, but if you want to learn more about this, look into classifier free guidance, or I'm happy to answer any questions after this. So far, so good. feel free to start asking questions on the chat if you like, and I can actually stop and try to answer those. I know we're actually covering many concepts here. Classifier-free guidance, just to dive into this a bit more. We'll try to predict the noise by trying to predict the noise if we weren't conditioning the output and trying to understand the direction where we need to go so as to get the text. Let's imagine a text prompt saying I want a woman, like we're actually seeing here on the right. We try to guide that using usually clip. That's what's used in the original paper. So we'll be basically comparing the denoised image with we'll do similarity with the text prompt that we're actually using as control in all of this, and we'll try to guide the reverse diffusion process into the direction where we have the denoised image closer to the text we're actually trying to be closer to. And just a few important concepts and hacks or tips you need to be really aware of if you're actually going to be working with this in production. It's LoRa. This also applies to LLMs, actually. This is really useful to actually get a bit more control on the model's output without training on huge datasets. Remember that for all of this, we're actually working with huge pre-trained models in 99% of the occasions. So we'll be basically using a smaller model that's trained in parallel to the pre-trained model. So we'll be basically having a single input, that's X in this image on the bottom. We'll be running that through the pre-trained weights that are actually frozen in this training process, and this smaller network that we see in orange on the right. We'll be just adding the outputs, and with this we actually get the advantage that by training a way smaller network with way smaller data than the originally needed for the training data set that trained the pre-trained model, we can actually control the output, and this is really good. For you to get an idea on how a few numbers from this in production, one of the pre-trained models, the one that we see in blue on the left, that can actually wait from 2 gigabytes to 6 gigabytes. And using LoRa, we can actually use models that can actually create amazing outputs with just 100 megabytes. In production, we'll be using the two of them. We'll be just training the one on the right for this. And for you to get an idea of real-world outputs from all of this, take a look at the image on the middle. To the left and to the right, we'll be using LoRa in the positive direction and negative direction in a way. So with LoRa, we can actually learn something, in this case, details. And you can see the image on the right actually has way more details than the image on the middle. And we can also use that to go in the opposite direction as we're actually doing in the left image. Other examples from this, we can actually use LoRa to teach new things to the model. So we actually taught Rihanna and use just a few samples of images from her to train these models, and we can use Rihanna to generate outputs, caricature effects, and the model already knew about, for example, Margot Robbie, as we're actually seeing here. We can actually add the caricaturize effect with this, or the Salvador Dali and melting clocks for that as well. So we have LoRa as one way of controlling this with much less training data as the original models. The other thing we can actually use is Dreambooth, and here we actually have some images from Vincent. This is the cat from one of the guys in the team, and we use those training images, only 10 of them, and the training script is available in Hugging Face in case you want to take a closer look at that. And we can generate these outputs we see on the right with different prompts. This is done by actually doing some fine-tuning on the model and actually teaching the model a new vector, a new key that we actually learn to use afterwards. So you're in a way teaching the identity of something new that the model didn't know before, because the model knew about cats, but it didn't know about Vincent, for example. and we only need 3 to 5 images of Vincent the cat in this case, or the dog in this new example, to actually fine tune the model, and then we can actually use that new concept that the model has learned to actually generate new images that really do a great job preserving the identity of the subject we actually want to teach it. It's great with objects, it's great with persons, it's also great with pets. And that's another hack. So we have LoRa, we have Dreambooth, we also have textual inversion that in a way tries to do something really, really similar to Dreambooth. Here it tries to exploit things that the model might already know, that it's really not that aware of, it actually knows them. So we're actually trying to inject via tokenizing a new concept, in this case S, that we're actually seeing in this example. S is a clock. We're trying to find the exact location of S in the vectorial latent space after encoding all of this, and then after getting to know that exact embedding, we can actually use that to generate new things. And this can actually do a great example, trying to change outputs as the ones that we're actually seeing here. We're for example, teaching the few images on the left, and we're trying to invert that. And we're actually talking about textual inversion because with text here, the photo of S is the text. We're actually trying to invert that into the latent space that we work with to find the exact location. Once we know that, we can use it as we please and move that in multiple directions. We can generate, for example, Elmo sitting in the same pose as S, and really does an excellent job doing that. Or we can actually generate app icons for that. And this can also be done to actually remove biases. For example, because with just a few images, we can actually teach the model to a new concept, and we can apply that as we please. How we're actually using this in production, we're actually trying to use this to remove some bad examples from what we generate ourselves as part of this training and inference pipeline. And we're actually using textual inversion to try to avoid some of these bad examples we know that our model is capable of. And I was just talking about a few moments ago about this virtual trainer application. You can see here the applications in some of the low-level details we need to work with. And I mentioned a couple of concepts that in a way compete against each other. So we have textual inversion and Dreambooth trying to give us a bit more control. In case you're actually looking to use some of this, Dreambooth, as I was saying, is actually great with details, specific subjects, face, pets, objects. It really does an amazing job, and we see some images from Dreambooth on the bottom right here in this slide. Textual inversion has the huge advantage of being way smaller to actually deploy to a server in production. So we're talking about 30K against 2 to 4 gigabytes from textual inversion to Dreambooth. And this is something you really need to take into account. You don't need to load any additional weight of the model, and you can more easily combine different concepts that you want to learn about with textual inversion than with Dreambooth. It has lower hardware requirements, and it's also easy to have that negative prompt. Once I know the exact location of the concept I want to teach the model, it's easy to go into the other direction, as we're actually seeing here with the hands. So we taught the model about example, and we asked him to avoid that in the future. Another important concept, let me just go to one of the questions. Is it possible to get a real-time application for try-on Cloudflare? Depends on what you actually call real-time. We're actually doing this real-time. It has some latency, of course, and depending on the hardware that you're actually talking about, it can be a few seconds, really not too much seconds, to a few minutes if you actually don't have enough compute power. Another important concept in case you want to control the output of the models, and I'm talking about controlling the output, that touches with some of the things that Harrison was saying a few moments ago. You need to be really safe when you deploy these things to production, and being safe in a way means controlling the output. So you need to be really careful with that. So we have ControlNet as another alternative to controlling the output. And here you basically clone the network and you have a frozen version that's already pre-trained of the network. Let's say one of these diffusion models, these foundational models, and you have this model on the right where you inject the control, use serial convolution layers to try to, when you start training, because you'll be training this new model that's in parallel with the other, you'll be adding the outputs like you're actually seeing here. It's easier to see that on the left. The image on the right, it's a bit more comprehensive of what's really going on. So you'll be training with images. Initially, at the beginning of the training, you'll just be using the pre-trained models. So you save a lot of time because the first images are really high quality. And as you have this serial convolution on the right, you initialize this to 0 initially. You'll be training that, you'll be changing those weights from 0. And so you'll be starting to see the effect of what you want to teach the network as training progress. Let me try to show an example of this in production. Again, this trial application. Without ControlNet, we actually see these failures in the image, as we see here on the left. With ControlNet, we can actually get the outputs on the right. We're actually seeing multiple training epochs on this. And how we're actually injecting the control is with this canny image that we're actually seeing here. It's really not that hard to actually try to do that with your own images. There are a lot of pre-trained models and also training scripts you can try to leverage for that. The input images are the ones that we see on the left. So with the person and with the garment, that's our input to the model. We inject this control, that's the canny image. And with that, we can actually get this output we see on the right. Hope this is clear. This is a bit of a complex concept, and I'm going a bit too fast, but I just want to give you an overview of all of these things. And a summary on all of these things, real-world applications require not only generative AI models, but you require a lot of additional things you need to take into account. Control being a huge part of all of that. If you're looking to generative AI applications, GAN networks, they're really amazing, but they don't have the level of detail that Stable Diffusion, as one of these more iconic models, has. And this can be a really slow process, so you really need to take into account hardware, what you can actually parallelize if you want to move this to production. And you need to take it into a closer look into textual inversion, LoRa, Dreamproof to personalize the model. That's to control the output and also control it for that. With LoRa, you can also reduce significantly the cost of fine-tuning your own diffusion models. And just to show you some real-world applications, this is the output we're actually getting. And I know you can't actually see the detail, but these are really high resolution images where I'm not sure if you can actually see this, but we're actually creating the skin tone on the arms of this person. And that's really hard to achieve. You remember all of the biases we can actually have on our training datasets. And just some final thoughts in all of this. This is evolving really, really fast. It took 4 years to get from this pixel image on the left to this GAN outputs that we see on the right. And it took about the same amount of time for diffusion models to actually get to this level of quality we're actually seeing on the right. This is a fairly known image. We're just adding the image on the right. In particular, these diffusion models have evolved really, really fast. In just a couple of years, we moved from what we're actually seeing on the left, this is BQ GAN, to these diffusion models we see on the right. With all of this, and I think this is also shared with LLMs, we can have mind-blowing results. Be careful because they're really, really expensive to train, especially train from scratch, and you'll need lots of training data. And the main challenges we see when moving these things to production is that they're really, really hard to control the output, and that people want to be safe when actually deploying these things, and that's really not easy to do. And that's just what we wanted to cover here today. I'm open to questions right now. I know that might have been a bit too fast, but I wanted to save some time for this space as well. Any questions, guys? how hard do you foresee that we can have any combination of backgrounds and products dynamically generated? I think we can actually see that right now. Let me just thank you for the comment. We can actually see that right now. It's just a matter of combining these things and having applications that really return on the investment, because hosting some of these models, it's really expensive. Sometimes people want real-time results, and that's even more expensive. So we can actually get that depending on your data set, specific needs. Might be a bit harder to control the output, but I think you can get that right now. Any other questions? It's another one. Did you try? I personally didn't try Hyper Dream Booth, but some of the guys in the team actually did. Even one of the guys in the team actually collaborated with Dream Booth. It's really active on Hugging Face. I hear that the results are really, really good. We actually had to go with a different path in the projects that were actually working with all of this, because we had these real-time requirements that actually, and also tried to get the cost a bit down. That made that LoRa made a bit more sense. Also text conversion. What are good resources or books to learn about this? Books. This is a fairly novelty space. I would recommend you actually following Hugging Face, following Arxiv. Many papers are being published right now regarding all of this. There are some companies like Stability, Mosaic, that you can actually try to learn a bit more about what they're actually doing. And I would just try to follow people that are actually working this. Meta is releasing a bunch of stuff, not in particularly too much in this space, but there are some of the guys to follow that you'll learn a lot about. When you say expensive, general idea of the we're talking about thousands of dollars per month. This again depends on your application. Just hosting one of these models, we're starting to see some platforms like Hugging Face allow you to host this in a really cheap way, but it actually costs them a bunch of money to have those servers up and running. So we're talking about GPU instances with A100s or stuff like that. So we're talking about, depending if it's reserved or not, and a few additional things, but a few $100s at the bare minimum per month. Thank you all for joining us. I think we don't have more questions. Happy to answer any additional questions that you have. I'm going to leave our email in the chat in case you want to reach out with more questions. Thank you very much for your time today. We were really happy to have all of you here, especially after this hour. Enjoy.